Science, and welcome to our final conversation about electricity, topic 3.3, measuring energy input and output. In the last video, in topic 3.2, I introduced you to the official concept of energy. We've been discussing energy on and off throughout the year. Unit B, we discussed it with the chemistry unit. We've discussed it quite a bit here with electricity and how electricity can be converted into other forms of energy. So this is a concept that is not new to section 3.2, but we officially gave a designation for energy, which is the ability to do work, and energy is measured in units called joules. Today's lesson is going to be the math component of how to calculate energy. How do we use math to calculate the energy being used by a device? So this is sort of the second half of our math component to this unit. We've already discussed the mathematical relationship between voltage, current, and resistance. Today we're going to be discussing the relationship of energy and its relationship to power and to time. And there will be a connection back to those variables about voltage, current, and resistance, which I'll get to in a couple seconds. But so I mentioned that there is a relationship between energy and power. So maybe we should start with our discussion with power. Some people think maybe power and energy is the same thing. It's not. Again, energy is the ability of something to do work. Power is how quickly a device can convert energy over a period of time. We discussed, the power of a light bulb, the power of a speaker, the power of a car's engine. How powerful the light bulb is going to determine how bright it is, right? How powerful the speaker is determines how loud it is. The power of the engine of a vehicle determines how fast it can accelerate. So, and in all these cases, the more powerful they are, the more energy they're going to require, because it's going to convert more energy over a specific amount of time if it's more powerful. So power is measured. So first of all, power is the ability of a device to convert energy over amount of time. And we measure power in units called watts, and W-A-T-T-S. These are named after a scientist by the name of Watt. Here's another unit in the electricity unit named after a famous scientist. We have ohms, we have amperes, we have volts. All of these are named after famous electrical chemical scientists. So in the case of power, the 1 watt is equivalent to the ability of a device to convert 1 joule of energy. Remember, we said the joules were the units for energy in 3.2, in 1 second. That would be the equivalent of 1 watt. So in order to calculate power, we have to be able to calculate it, because sometimes we don't know what the power of a device is. But in some cases, the questions will give you information about the electrical circuit that device is plugged into. And from that information, you can deduce or calculate its power. So power is calculated by multiplying the current of a circuit to the voltage of a circuit. So basically, power is equal to IV. So P equals IV. Again, a formula which you're going to be provided. It's in the data sheet. You may have noticed that it was on your data sheet in the last quiz, in the section 2 quiz of the unit, where you were doing some calculations already with voltage and current and resistance. But this formula was also provided for you. So you don't have to memorize the formula. You just need to know how it kind of works. And again, so let's do an example with this. So let's say I've got a device that maybe I know. In this case, let's say I've got a device that I know the power of, and I want to calculate how much current or how much voltage needs to be on the circuit in order to make this device run with that power. So, for example, I've got a curling iron. This one's in your notes right here. I got a curling iron that's using 1,200 watts of power, and it's plugged into a 120 volt outlet in your house. The question is, can you calculate the current for me? Now, that information is on this slide. So if you're following along at home, you've already got the answer in front of you. But maybe see if you can calculate it if you haven't seen the slide yet. Take a look and see if you can calculate it. Pause me if you need to. I'm going to give you the answer right now. So I'm going to use my formula of power. Power is going to equal, again, current times voltage. What variables have I been given? Well, I've been given the power of the device. So I know the power is 1,200 watts. And the current I don't know, because I'm having to calculate my current. And my voltage is going to be 120 volts. By the way, for this equation, be aware the units are always going to be standardized. Power is always going to be in watts. Current's always going to be in amps. And voltage should always be in volts. So if you have any kind of a question where you've got kilovolts or millivolts or kilowatts, or you have to convert them to their baseline unit of watts or amperes or volts. Otherwise, you're going to have issues if you're trying to multiply a kilowatt with an ampere. You're not going to get an answer in watts. You'd be getting an answer then in kilowatts. So it's very important that you kind of keep that in mind, right? So, anyways, in this case, I have to calculate I. So I is going to be basically 1,200 watts divided by 120 volts, and that's going to give me a current of 10. But again, 10 isn't a complete answer. Some of you may have found that out on the last quiz. If you didn't put your units in, you got docked marks. You have to include units for each of these variables, or each of these, like for power has units, right? Current has units, voltage has units. They all have a unit involved. It'd be like giving me, what's the distance? Well, it's 10. What, 10 miles, 10 kilometers, 10 meters? I need to know what the units are for that measurement. Otherwise, it's useless to me. In this case, the answer is going to be, in fact, 10 amps, and which is basically described to you on that page right there below. Let's do another one. Let's take another curling iron, but in this case, I'm going to give you a curling iron that I don't know the power of. We're going to make this one really easy. I'm going to keep my formula up there because you pretty much know the formula we're going to use. What I need to know in this case, I'm going to calculate the power, because my board almost falls again. This is a very tricky board, so it does sometimes fail me, and it just almost failed there. What's the power of the curling iron? I got to run some numbers here, so just give me 2 seconds. What's the power of the curling iron? I'm going to say the curling iron is now plugged into a socket that is 120 volts. Curling iron. Curling iron has, and we're going to say it's going to has 10 amps of current running through it. Okay. Kind of ran out of space. So I'm going to read you the question. So, for example, a curling iron now has 10 amps of current running through it, and it's plugged into a 100-volt outlet. Let's calculate the power of this curling iron. So let's pause me right now, see if you can calculate that based on the information I've given you. So again, 10 amps of current, 100 volts of 100 volts of voltage that it's plugged into. All right. How would you calculate it? Well, again, it's going to be P equals current times voltage. I've been given both those variables. I know my current is in 10 amps. I know my voltage is at 100 volts. There's no conversion. There's no milliamps there, or kiloamps, or kilovolts or millivolts. So I know that all my units are correct. Anything I multiply here is going to be automatically in watts. That's going to be my power in watts. Well, if I take 10 times 100, that's going to give me 1,000 watts. You could convert that if you wanted to. You could convert that by dividing by 1,000. Technically, again, 1,000 watts is going to be equal to a kilowatt, no different than, 1,000 meters would be equal to a kilometer, right? So it's sort of the same idea there. So there's another example there. So power can be converted by calculating. If you know the current or the voltage, you can calculate the power of a device. Now that you know how to calculate power, you can sort of now calculate the energy usage. If you know the power of a device, and if you know how long the device is running for, how long the device is converting the energy, then you can basically calculate the energy usage of a device. So in order to calculate the energy usage of a device, we're going to use another formula. This one is going to be E equals P times T. So energy equals power times time, which kind of makes sense because I just said that 1 watt of power converts 1 joule of energy in 1 second. So we know that there's a relationship between time and power. In this case, the longer a device is converting energy, i.e. power of the device, we know it's going to use more energy. It's going to output more energy, or use more energy so if I've got a speaker that's running for 3 hours, converting that electrical energy to sound energy, that's going to be using what's the electrical energy we need to actually to make that device continue doing that power conversion, right? That conversion of energy that's making that speaker work. So in this case, we've got energy, which is going to be measured again in joules. I mentioned that the units for energy are joules. And we're going to have a joule is going to be equal to 1 watt converted in 1 second. So, sorry, 1 watt of power being used for 1 second. That's a joule. So, for example, if I had a 1 watt device that was running for 1 second, I would basically be using 1 joule of energy. Again, the units have to be specific. You can't have kilowatts here or hours or minutes or, hours or minutes or days. The time has to be in seconds in order for this calculation to work. So you've got to be really careful. And this is where they're going to probably fool you a bit by converting your time units from maybe seconds to minutes or, in hours. So you have to be able to convert from hours to minutes to seconds. And remember, when we're converting minutes to hours to seconds, it's always a factor of 60, right? So if I've got I got 3,600 seconds, that would be then, if I divided that by 60, I would have then 60 minutes. If I divided that 60 minutes by another 60, that gives me 1 hour. So essentially 3,600 seconds equals an hour, right? So you have to be able to do some of that conversion there. And that's, a little bit tricky because it's not base 10, but in theory, you've been converting and knowing how to convert time for quite some time. It's a factor of 60 if you're dealing with hours to minutes or minutes to seconds, right? It's just a matter of, am I multiplying or am I dividing? I always have more seconds than I would have minutes. I'm always going to have more minutes than I would have hours, right? So you know that if you're going from hours to minutes, you'd be multiplying. If you're going from minutes to hours, you'd be dividing. Or if I'm going from minutes to seconds, I'd be multiplying by 60. If I'm going from seconds to minutes, I'd be dividing by 60. So I'll give you an example of that right now. Here's the example I'm going to give you. I've done a trick. The time units are wrong. I've got a light bulb that's rated 150 watts of power right here, and it's on for 8 hours. Calculate the energy used. Now, a lot of you would run right to the gusto and say, I got 150, I got 8, I'm going to multiply those together. I'm going to get myself an answer of 1,200 watts. Yay for me. No, that's not going to work. Because again, when we're dealing with joules of energy, and that's what we're dealing with here, we need to know how many joules. It's asking specifically how many joules of energy are used. My units have to be in watts and seconds. So the trick to this question is converting 8 hours into seconds. So I know that in an hour, there are 3,600 seconds in an hour. How do I know that? 60 seconds in a minute. There are 60 minutes in an hour. 60 times 60 is 3,600. So I need 3,600, but I've got 8 hours. So it's 3,600 times 8. That's going to give me a conversion of 28,800 seconds. So that's the toughest part of the question, was converting hours into seconds. And you can see that conversion right here on my slide. If you didn't really see that up on the board, take a look at my notes. It's all there. I'm using the example that's in the notes. And I know that I've got 28,800 seconds. My power conversion is good. I've got watts, so that's going to be fine. So I know that energy is going to be power times time. So I'm using this formula here, E equals P times T, right there as I walked out of my frame. So I've got power times time, so I got 150 watts times 28,800 seconds. If I multiply those two together, I'm going to get myself a really big number, which is going to be 432,000 joules. Now I could divide that by 1,000. I could convert it to kilojoules if I wanted to make it less onerous, but this question on the board specifically asks for joules. But if I had to convert to kilojoules, it's simple, divide by 1,000, and that would give me an answer of 432 kilojoules if it was asking for kilojoules. Okay, so that's an example of how we calculate power. You can see here, though, that a light bulb running for 8 hours, in joules, the numbers get really, really ugly. They kind of get really ugly. Did I actually calculate that wrong? I'm going to go back for a second. Hold on. I think I may have calculated that wrong. Just give me 2 seconds. I was looking at my slide, and now I'm going to double check this. Live TV, gotta love it, eh? Let me go back. Let me go one more time here. Come on, one more time. Oh, I did. I see. I forgot. I forgot a zero. My apologies. I looked at it and I didn't look at it really carefully. There's a 40 there. So it wasn't actually 432,000. It was 4,332,000. I just didn't read the 10. Sorry, that was my bad. So again, my kilojoules are not going to be 432. I have to add another zero there. So it's going to be 4,320 kilojoules. Pardon me. That was just me looking at the screen really quickly and just not reading an extra zero. But again, you can see how quickly that can happen if you're off your calculator. If you don't read 10, your math can go bad real quick. So there you go. There's that. Okay. But as I was saying, the energy usage of a light bulb over 8 hours is a very large number. These are not really easy numbers that we can use, let's say, with our household. Our house uses a lot of power. This is only one light bulb. Imagine all the devices in your house using the power all day long. There's got to be other units we can use for energy, and there is. When we're dealing with household power, you may have heard of this unit. There's also a unit known as a kilowatt hour. Kilowatt hours is a unit for energy that's used for large consumption of energy. It just makes your numbers smaller. And if you go to your outside of your house, you've got a device on the outside of your house that actually spins. You may have noticed it, and it's actually spinning and calculating how much energy your house is using. If you look at that device really closely, you'll notice that it's actually being measured in kilowatt hours. So that's your power bills. When you get your power bills every day, or not every day, every month, they're calculating how much energy is being used. It's kind of funny because we call them power bills, but really they're actually energy bills. How much energy are we using in the house, even though we do call them a power bill? So when we're dealing with kilowatt hours, the formula is still the same. We're still going to use P times T, except now the units for power and time are going to change. To calculate joules, we're using a power unit of watts and a time unit of seconds. That would give you a joule. To get a kilowatt hour, the beauty of the unit is it tells you what the two units are that are put together. It's a kilowatt times an hour. So basically, we're going to up our power, we're going to go from watts to kilowatts, which is we're going up by a factor of 1,000 in how much power is being used in this unit of measurement for energy. And our time factor goes up by a factor of 3,600 because we're going from seconds to hours. So it's going to take these really large numbers. If we were to calculate all this in joules, we're going to calculate much smaller, much more manageable numbers. So just keep that in mind. When we're dealing with small amounts of energy usage, we're going to use the units of joules, which are watts times seconds. If I'm using large amounts of energy, I'm going to be using what are called kilowatt hours, which are kilowatts times hours. Now, when you get a question about energy, really important to read. What's the question asking you? Is it asking for the energy in kilowatt hours, or is it asking you for the energy in joules? Depending on what it's asking you, your units for power and time have to be factored in, right? So you can't just, well, hey, they're just giving me numbers. I can just take the two numbers and plug them in. Careful, they might try to trick you by giving you the wrong units. You have to convert to the right unit. So it's very important that you keep that in mind. Joules, watts times seconds, kilowatt hours or kilowatts times hours, all right? That is not going to be given to you in the data sheet. They give you the formula, but you're responsible for remembering that a joule is a watt times a second and a kilowatt hour is a kilowatt times an hour. That you need to memorize. Otherwise, you're not going to know how to plug in the variables into the formula like you would need to. Let me give you an example. This one isn't in your notes, so you're going to pause the video and kind of maybe see if you can calculate this along with me. I've got an example here. Calculate the kilowatt hours of energy used by a device, or a speaker in this case. It's a 100-watt speaker, and it's going to be used for 120 minutes. I want you to calculate the energy for that device. Pause me right now, and I am going to give you a hint. There are 2 unit conversions that you have to do in order to make this question work. If you don't convert the power and the time, you're going to get a totally wrong number. Do not calculate 100 times 120. If you do that, you're going to be dead wrong. Pause me right now and see if you can do the calculations. I'm going to come right back and show you how to do it. All right, here's how you do it. I'm going to use my calculation for energy, which is power times time. My power in this case is going to be 100 watts, but I know that I'm trying to calculate kilowatt hours, so I got to convert watts into kilowatts. I'm going to do that by dividing by 1,000. 1,000 watts in a kilowatt. So I'm going to basically divide by 1,000. This is going to give me my power rating of 0.1 kilowatts. That would be my power. So there's my first variable to the right unit. So I said, remember, if it's kilowatt hours, you have to convert it to kilowatts. Second one is minutes. I don't have kilowatt minutes. These are kilowatt hours we're dealing with. So I have to convert my minutes to hours. 120 minutes is going to be equal to 2 hours. Again, how do I calculate that? I know there's 60 minutes in an hour. There are 60 times 2 is 120, right? So in this case, all I would have to do is divide 120 by 60 because that's how many minutes are in an hour. That would tell me how many hours are in 120 minutes. So it's 120 divided by 2. That's going to give me a total of 2 hours. So if I calculate these two suckers together, it's going to be a nice, small, manageable number. It's going to be 0.2 kilowatt hours, which is certainly different than if I would have calculated 100 times 120. That would have given me like 12,000 kilowatt hours, which is completely wrong because this is not kilowatts, and that is certainly not hours. So that's the trick to these questions. The formula is easy. It's converting the units that are going to be the issue that you have to kind of keep an eye on. So keep that in mind, please. All right? Okay. All right, so those are the calculations for energy. Let's talk about energy conversion itself. We talked about that last video, 3.2. We talked about how energy conversions, energy, basically electrical energy gets converted by a load or a resistor to another form of energy like heat or light or sound. There are rules behind energy conversion, and we call these the laws of thermodynamics. Now, there are two that you should be very familiar with, and they do kind of crop up from time to time obviously in Science 9, but we discuss them in Bio 20. I discuss them in Bio 30. I discuss them even in Science 30. I discuss them quite a bit. So these are concepts that you're going to hear about a lot as you move through science. The first law of thermodynamics is known as the law of the conservation of energy. And this is an easy one. Energy cannot be created or destroyed. It can only be converted. So if you have a resistor in a circuit, for example, right, that resistor cuts the current down, that converts electrical energy, the movement of those electrons into another form of energy. It could be thermal, could be light energy if the resistor kind of lights up, glows if it's getting hot. That's the conversion. So we're not losing energy. We're just taking electrical energy and converting it into something else. So that's what the first law states. You can't destroy energy. Energy is all around. One form of energy gets converted to another. Plants, photosynthesis, right? They take solar energy, they convert it into chemical energy in the bonds of a glucose molecule as part of photosynthesis. That bond of energy in the glucose is essentially the conversion of solar energy into chemical energy. It's still energy. It's just converted from one form to another. The second law is what I want to spend more time on, though. That conversion I just talked about is never 100% efficient. There's always a loss of energy, not a loss, but there's wasted energy. So for example, if I've got a light bulb is designed to light up, right? And it's essentially taking electrical energy, converting it into light energy. But we also know that if we touch a light bulb, even LED bulbs, not as bad as the old incandescent bulbs, but light bulbs, if you leave them on for a long period of time, will get warm or hot, depending on what kind of a light bulb you've got. That heat is a form of energy that's been converted off the electricity, but it's not useful energy. We don't need the light bulbs to be hot. We just want the light bulbs to produce light energy. If I can take all my 100% of that electricity and convert it to light energy, it would be a much more efficient device. But there's always going to be some wasted energy. We sometimes refer to that as friction. If you have, let's say, friction because of resistors in a circuit or whatever. But so the efficiency of a device is determined by how much the initial input energy is in relation to the useful output energy at the end of the process. So, for example, we would use, there's a formula coming up. Go figure. You can calculate this, folks, and it's actually pretty straightforward. It's sort of like calculating a mark on an exam, all right? So let's say you went into an exam. The exam was, 100 marks, and you got 50. Well, how would you calculate your percentage on that exam? You would take the 50, divide it by 100, and then multiply by 100, right? That's how you calculate your percentage, right? Let me give you another example. Let's say I have 12 out of 25. I would take 12 divided by 25, multiply it by 100. I know what my percentage was on that exam. That's 48%, right? It's going to be 0.48 times 100 is going to be 48%, right? So you all know how to calculate percentages on exams. That's what efficiency is. The useful output energy is like the mark you got on the exam. That's the useful mark that you got out of the exam. If you were 100% efficient on that exam, you would have got all the questions right, but you didn't, right? You maybe got only 3/4 of them right, or you got half of them right, or you got 90% of them right. You're not 100% efficient on the knowledge that was on that quiz. Well, there's devices so let's say the light bulb, for example, let's say it only produces 60 watts or 60 going energy here. Let's go 60 watts of energy is what it produces in light energy, right? 60 joules, let's say. But in order to make that 60 joules of light, we had to put 100 joules of electricity into that light bulb to get that 60 joules. The other 40 joules might have been lost as heat or other useless energy forms that didn't really help us create the light that is what we wanted that load to do. So in this case, your mark, the output energy of the light bulb, let's say it's 60, and that's your output energy. And then you've got your total input energy. Your total input energy would be the raw score on the exam in your case, or in the case of the light bulb, it would be the amount of electrical energy that was put into the light before we had the production of the light in the light bulb. But the key here is we have to calculate our useful output energy. What if I had a blow dryer, right? What's a blow dryer designed to do? Dry your hair, right? That's the useful output energy of blow dryer is thermal energy. But what else does a blow dryer do? It makes a lot of noise. That noise, that's the wasted energy. That's energy that is not being used for what, it doesn't do us any good. The sound that's being produced by the blow dryer is a conversion of the electricity into a wasted form of energy that we can't use. So the louder the blow dryer is, in theory, the less efficient the blow dryer is. If you have a quiet blow dryer, you might have a more efficient blow dryer because you're not wasting energy in other forms that are not useful. So in the case of the light bulb, the useful energy is the light energy. The heat that's being produced by the light bulb is not considered to be a useful form of energy. Let's take this into an actual example. There's a couple in your notes here. I'm going to pull one off and then I'll read the other one off the slide. I got an SUV, right? It's got an input energy of 675 kilojoules of energy, and it only generates about 81 kilojoules of useful energy, i.e. motion kinetic energy. What's the efficiency of the SUV? Well, I've just been told my useful energy is 81 kilojoules. So it's going to be 81 on the top, and I know that my input energy, my total input energy is 675, so it's going to go underneath. I'm going to multiply that by 100, and if I round that to my nearest decimal place, I'm going to get a percentage efficiency of roughly 12%. That's how you calculate it. Now, be careful. These units have to be the what? They have to be the same. You can't compare apples to oranges or oranges to apples. I can't have joules and kilojoules and just run them into the equation straight across. If I've got different units of energy, I have to convert them into one. They have to be the same. Let's say this was in joules, for example. Let's just kind of play devil's advocate here. That isn't going to work. Let's try this the other way. Let's say that I only produce 81 joules of useful energy. Now what I've written down is not going to work. I either have to convert my kilojoules to joules or my joules to kilojoules. It's my choice. So I could divide this one by 1,000 to get it into kilojoules, or I can multiply this one by 1,000 to get it to joules. I'm going to multiply by 1,000 because that's a little easier. So that's going to basically give me, this would now be my equation. 81 joules divided by 675,000 joules. Well, you can tell right away the efficiency is not going to be anywhere close to 12% now. I have to take my 12 and basically I have to reduce it by a factor of 1,000. So if I took 12 and divided by 1,000, I'm not mistaken, it's going to give me a percentage that's going to look something like that. 0.012. You can do the calculation at home. But again, Making sure that your units are the same is very important when you're doing these efficiency reactions, or these efficiency equations, pardon me. The next one that's on there, we got a more efficient vehicle. Now we got a hybrid. We got a hybrid vehicle that's now going to generate, and I'm just going to run my numbers off the board here. It's going to generate not the 81 kilojoules. It's going to generate 195 kilojoules of energy. So again, what would I do here? Well, again, I'm going to have my useful output energy, which in this case is 195 kilojoules divided by 675 kilojoules multiplied by 100. That's going to give me an efficiency of roughly 28.9%. That's how you calculate efficiency. So 3 equations coming at you today, a lot of equations. You have the efficiency equation that I just ran you through, useful output energy divided by the total input energy multiplied by 1,000. You got the calculations for power, which is going to be calculated by multiplying your current times your voltage. And then you're going to be able to calculate energy by multiplying power times time. That's either going to be watts times seconds to calculate your joules, or you're going to get kilowatts times hours to calculate your energy in kilowatt hours. You know it's coming. Math is coming your way now. There's actually 2 pieces of homework for this section. A lot of math in this one, pretty much all going to be calculational math, so make sure you got your calculator on you. I want you to do questions 1 to 11 on page 338 of your textbook, and at the bottom of the video here, check down below, there is a link in the description to the energy input and output worksheet. Both of those are going to be due for our next class, so get on those and get those calculators working. Make those calculators, convert some of that energy over periods of time. We'll see how much energy and power your calculators are using. That's it. You know what? This is the last video for the electricity unit. Thanks for joining me. Join me again for our final unit coming up next time. That's going to be on space exploration. Very much excited to discuss the history of space exploration and space science. Some really cool stuff, and it's always an evolving branch of science, and there's always new stuff coming out. So I'm very much excited to be sharing that stuff with you next time. So good luck with all this, and we'll be seeing you fairly soon after your unit exam. We'll be tackling some space exploration and astronomy. Take care.